Hello everyone, welcome to Mark 1 Design EMC video channel. In today's session, I'm going to present a topic which I did about 1 month ago for interference technology, and the topic is fast circuits for fast cars, a review of fast switching circuit boards and their EMC impact on electric vehicles. So I thought I might just share this presentation with an even wider audience on the internet. Just quick introduction of our company. Mark 1 Design is a UK-based EMC consulting company. We are specialized in EMC pre-compliance design and troubleshooting. In terms of areas we cover home appliance, professional, industrial, and automotive. We certainly see an increased number of inquiries from the automotive world. This is particularly in line with the recent PHEV and EV development. And we predict that this section is actually going to expand in the near future. So that's where we put our focus on. In today's presentation, the agenda is shown as below. First, we'll have a very quick EV review and its associated challenges, with a particular focus on the high voltage system in the electric vehicle. Because the topic is about the switching event and its EMC impact, so we're going to look at a switching event from both the time domain and frequency domain point of view. We will present some practical examples to explain the coupling mechanism in a typical fast switching system. And finally, before we conclude, we will have a light touch of a topic on the grounding of a system. Here shows you some pictures. On the left is the news about Foxconn is going to make an EV system. This is interesting because Foxconn is traditionally a mobile phone manufacturer. It is not a surprise for the reason we'll explain later. And the demand for EV and hybrid vehicles is going to increase by a big percentage in the following years. The new philosophy, the new design philosophy of making an electric vehicle is quite different with the one that making an internal combustion engine vehicle, because weight is perhaps is one factor that is becoming very, very important. Traditionally, for internal combustion engine manufacturers, weight has not been a big problem. We've seen cases where manufacturers put a lot more extra weight on a vehicle for safety reasons, for acoustics performance reasons, or for other reasons. But you cannot do that on an electric vehicle simply because the range is perhaps the most important thing for an EV, and consumers pay money for extra mileage that you can provide. So as a result, manufacturers has pushed their tier 1 suppliers to give them a smaller, lighter, and more compact component so they can fit in their vehicle. Together with electric vehicle, of course, is the autonomous driving. Then this requires EMC, functional safety, and cybersecurity. Functional safety and cybersecurity are not in scope of today's topic. And of course, a vehicle is well connected. It's like a moving mobile phone, let's say. So that's why I said we're not surprised that Foxconn is going to get into this market. And very similar to all the consumer electronics, vehicle manufacturing is also a very cost-sensitive business. So every penny, every cent counts when it comes to making a vehicle. That's something we shouldn't forget. Here shows you a typical high voltage system in an electric vehicle. We've got the onboard charger, then together with the battery pack. Often within the battery pack, you have a very clever battery management system to monitor each individual cell for safety and performance reasons. The DC-DC converter replaced the traditional role of a traditional alternator. So it converts higher voltage coming from the battery pack, often in a range of 400 volts and 800 volts down to either 48 volts or 12 volt system, or sometimes both. The most important unit in the electric vehicle is the motor, because it gives you the performance and range. So motor is quite important. And we've seen cases where heater elements and compressor, these are the key elements in a HVAC system. Now they are using high voltage components, simply because high voltage components give you much higher efficiency compared to low voltage modules. It's worth mentioning that if you look at, let's say, example of onboard charger, if you look at the filter components, you will see that the filter components actually take perhaps more than 30 or 35% of the overall volume and weight of the module. So you can see that actually manufacturers put lots of effort just trying to make sure that all these components are compliant with associated EMC standards. So the challenges associated with a high voltage system are, first of all, we have to understand that going for a higher voltage, we're talking about even higher than 600 volts, so 800 volts perhaps in the future, 1,200 volts, is a design trend for obvious reasons, because for a given power rating, if you have higher voltage, then you have less current, and less current means less I²R loss, so your overall system efficiency improves a lot. But high voltage system has its associated higher dV over dt issue, which represents a higher E field, electric field in your system. So that's closely related to the EMC part. Another challenge is high voltage safety requirements has put a limit for the leakage current that goes into the vehicle chassis. So for safety reasons mainly, that means you as a result, you will have a limited capacitance value that you can use for common mode filtering. And we all know that wide capacitance is very effective in the common mode filtering. So here, the diagram shows you what it means. Suppose you are designing a system and you try to upgrade the system from 400 volts to 800 volts. What does that mean for the common mode filtering capacitance that you can use? You can only use 25% of the wide capacitance compared to your 400 volt system when doubling the voltage. So you got, on one hand, you got much challenging problem to deal with, which is a higher dV over dt. On the other hand, you are really limited by the filtering methods that you can use. So that's a big challenge. And we've seen a lot more high voltage EMC standards coming in the next few years. One of them is high voltage, low voltage attenuation, which has already been adopted by many OEM manufacturers. And what about the challenges associated with high power? Well, high power, again, is also a trend, because with high power, you have much higher performance vehicle, right? But then higher power often means higher current, giving fixed voltage. And higher current means higher magnetic field in your vehicle. So that's the risk associated with EMC. And another thing is, with high power system, you have to bear in mind that it shares exactly the same noise limit value as the low power system. So for instance, here we demonstrate, this is a CISPA 25 class 5 conducted emission limit. Here's the values relating to peak value, quasi-peak, and peak, quasi-peak, and average. And as you can see, in a frequency range that most OEMs interested, sort of FM band, the current you measure on a 50 ohm load is 159 nanoampere, right? And this current limit is the same for 800 watts 48 to 12 volts DC-DC. It's the same for 600 volts to 12 volts DC-DC, and it's the same for 250 kilowatts electric motor. So all apply to the same standards, but obviously, when you have a much higher power system, then the challenge is greater compared to a low power system. And yeah, higher power systems often have higher level of transients. So we have a look at two practical examples of a fast switching circuit in an EV. So first of all is a powertrain unit, as we said, is perhaps one of the most important units in a vehicle. For powertrain unit, if we look at the fast switching circuits, we can quickly identify three areas. The main one is, of course, the power stage to drive the motor drive stage for the motor. In the past, these are high voltage IGBTs, but now they're replaced by silicon carbide device. With silicon carbide device, your switching frequency and your switching speed can easily double, triple, or quadruple of that of IGBT. And they can easily withstand the thermal performance. But the EMC performance will be much worse simply because of the high dV over dt issues. And then on the low voltage power rail, we often have a switching mode power supply that also has a very fast switching switch. And we've seen, for a system like this, you always have to design an isolation circuit between your low voltage part and high voltage part. And we've seen cases that the isolation chips itself actually has a lot of fast switching events there, and these can cause problems. So that's also an area that people sometimes ignore. And the second example, we show a DC-DC converter. So here is a simplified diagram of a phase shift full bridge DC-DC converter. So this is the converter between high voltage and low voltage. And again, we can easily identify the hot loop areas, which are associated with the high switching frequency devices. Again, these devices used to be MOSFET, and in the future it's going to be silicon carbide or GaN device. Yeah, so much faster. Here just shows you some future configuration of a DC-DC converter. Top side one is an Audi echrome DC-DC converter. As we can see, it's on high voltage, so it's the input filter stage. They're using multi-stage input filter, which consists of both differential mode and common mode. Yeah, and it's interesting to see that for the Y capacitor, they are using an array of ceramic capacitors. So in order to get to that voltage level, they put ceramic capacitors in series, but of course that will increase the ESR and ESL of the Y capacitor. So they also need to put a few series array in parallel to balance that. I think the main reason for this is just purely from cost point of view, as we stressed earlier. After all, vehicle manufacturing is still a cost-sensitive manufacturing business. So every penny, every cent counts. The bottom picture shows the DC-DC converter used in Tesla Model S, and the high voltage input filter stage is pretty much the same as the Audi one. Interesting here is on the low voltage filter stage, because here we're talking about 12 volts output with current rating from 200 amps to 300 amps. So any magnetic components you can use will be very big. Yeah. So often manufacturer, what they do is they use cores. Yeah, either ferrite or nanocrystalline cores, depends on the frequency range you want to filter out. And they put the cores along the bus bar lines. If you insert both bus bar lines into the cores, then you form a common mode choke. If you just put V bus plus and together with some capacitors after, then you build a LC filter low pass filter stage, which I think is exactly the configuration here shows in the Tesla module. Now we look at a switching event. First we look at the switching event from a time domain point of view. Here shows you a typical motor phase current. As you can see, if we look at the current, we can easily divide the current component into the fundamental component, which is associated with your motor speed, and then the switching component, which is associated with the PWM switching frequency, and the RF component, which EMC people are most interested. And we can even break down the RF components into two parts. First part is the broadband noise. So this is the noise actually, if you're using a spectral analyzer, you measure it and you see the noise profile from 30 megahertz to 300 megahertz. These are often related to the rise time, as we explained earlier, of a switching device. And we have higher frequency spectrum, which is larger than 300 megahertz, and this is often as a result of reverse recovery of a body diode or occasional electric breakdown caused by bearing current of an electric motor. The next step is we view a switching event from the frequency domain point of view. Giving a switch event such as this, if we do the FFT, we will find an envelope of spectrum such as this. The most two important points showing here are the two corner points. Corner point A is related to the duration time of a switching event, so which is also related to your switching frequency, let's say. Corner point B is related to how fast you switch your device on and off. So it's related to your switching speed. And from A to B, you have 20 dB per decade attenuation. But above B, you have 40 dB per decade attenuation. So of course, you want the 40 dB per decade because it's much easier to filter the noise. But if you want to have a much faster switching speed, so your rise time is reduced, then effectively you push this corner point B to a larger frequency level. So you have a minus 20 dB per decade rule off, which is much harder to deal with, let's say. The relationship between a time domain and frequency domain can be demonstrated in here. So this is a screenshot from Ken Wire's YouTube video channel. I put the video link here so you can watch it. It's about 3 or 4 minutes. So in this case, he demonstrated that the ringing and overshoot of a switching event is related to a frequency bump, that a resonance bump observed in a spectral analyzer. Yeah. So we talk about switching frequency and rise time. What's the relationship? What if we double the switching frequency of a DC-DC converter, let's just say? Generally speaking, if you double the switching frequency of a DC-DC converter, you will have at least 3 to 6 dB increase overall on your spectrum measurement, which is demonstrated here. So here we demonstrate 30 kilohertz and 60 kilohertz switching and its associated FFT analysis. How about doubling the switching speed? Well, as we explained before, if you double your switching speed, so in this case, you're from 125 nanoseconds to 62.5 nanoseconds rise time, then you will see the corner point B has been pushed to a much higher frequency point. So you got all this extra increase simply because of the switching speed increase. Here's a practical example demonstrating, what normally we do with all this time domain or frequency domain analysis. Often we get test results such as this, and we can quickly, just by looking at the waveform, and say, look, this first resonance point between 10 megahertz and 20 megahertz is relating to an IGBT switching, right? So this is a project of a electric motor drive unit used in a EV hybrid, I think. And then the second resonance point, which is about sort of 60 megahertz range, is related closely to the MOSFETs that they use for the switch mode power supply. So when you have a look at the EMC test result, at least you can quickly identify where the noise source are. This is a interesting case study demonstrating loop inductance causes ringing and overshoot. We've seen two cases actually now in an EV application where for the DC-DC converter design, they use TO247 devices. So in this case, they're using a TO247 MOSFET. The problem with TO247 package, as you can see here, is the actual long lead of drain, gate, and the source. These actual long leads is quite long. They introduce at least 10 nanohenry inductance. So in order to demonstrate this point, we built a very simple simulation model showing here. So in this simulation model, we use exactly the device provided by the manufacturer. We put some parasitic components in the simulation, because as I said, the leads easily introduce 10 nanohenry inductance, plus the trace and track on the PCB. So comfortably, we said 20 nanohenry between the electrolytic capacitor and device. And the package itself is quite large, and it's mounted onto the heatsink. So we give them 1 nanofarad as the parasitic capacitance, and then we just run this simulation model. Simulation model shows that this is the ringing observed on simulation model. If I measure the resonance frequency, it gives me about 20 megahertz ringing frequency. And this is what we measured on the actual unit. And you can see it is very similar to the simulation model, which indicates our simulation model works quite well. And just to double check, as we mentioned before, your time domain measurement has a relationship with your frequency domain measurement. So in this case, we put a current probe on the DC bus line, and then we measured common mode component. And as you can see here, on the 20 megahertz, we've seen a big resonance. So altogether, it makes perfect sense, and we know that's the long lead inductance are the problem. That's the noise source. And with the simulation, we can easily simulate that if we reduce the inductance, the parasitic inductance, say from 20 nanohenry to 10 nanohenry, and then down to 5 nanohenry, we can reduce the ringing by quite a lot. But the problem, as I said, is the intrinsic parasitic inductance of the device itself has 10 nanohenry. So obviously this 5 nanohenry is nice to have, but in reality, we cannot achieve it. So so what can we do? Well, what they should have done in the first place is they should never use a TO247 for such projects. I mean, it is, from their point of view, by using TO247, their thermal performance can be well managed. Cost of a TO247 is much lower than a surface-mounted part. And they don't need to put many, say, in parallel to share the current, So it's, for them, from thermal point of view, cost point of view, it looks like a good choice, but not for EMC. So that's the debate, if you have a design that later on has big EMC problems, and then that you're going to spend perhaps even $50 or $100 on some filtering component, and also filtering components are big and heavy, would you still choose the TO247 in the first place? I guess probably not. So here shows you configuration used in Tesla, I think. As you can see, they are using, this is a silicon carbide device, and you can see that they are using surface mounted type, and then they put many MOSFETs in parallel to share the current, hence to improve the thermal performance. And this also has very low inductance on their connection, so it's very good for EMC from EMC point of view. But of course, when clients have already had a system designed, and it's a late stage, you can't really afford to go back to say, shall we start designing from scratch? So in this case, what can we do? Well, old technology back in the 90s, it's called spike killer. So this kind of device is like a small ferrite ring that you can put through your long leads of a TO247 device. It acts like a snubber circuit. The little loop is very lossy, so in effect it damps the overshoot by quite a bit. So in case that you really can't find any other solutions, this might be an option. Yeah. Case study 2 is an interesting one. It demonstrates that sometimes a seemingly a small device seems like no harm, but actually can cause a big problem. So in this case, it's a current sensor device that is mounted on the DC bus bar of a battery pack that caused conducting emission issue, and also radiating emission issue as well. So here shows you the conducting emission test result, showing you, if you look at the measurements, particularly in the FM band, is exceeding the level by a lot. And we quickly identify that it's the current sensor itself has problem, because there's a small DC-DC converter, and that DC-DC converter happened to switch at the frequency the same as the CAN bus, and so it's been hiding there for a while. And if you look at the current sensor location, you can see it's easily electrically and magnetically coupled to the system, magnetically coupled with the DC bus bar, electrically coupled to all the nearby adjacent the cables. Yeah. And the supply actually did some work. For instance, they put a common mode choke on the 12 volts and ground line, but found there's no effect. Right? Well, this has no effect mainly because the common mode choke itself will be bypassed by this nearby cables, and also perhaps the little PCB there. So what the solution is we designed sort of like a two-stage filter with LC filter in the first stage, and then common mode choke on the second stage. But common mode choke needs to be along all the lines to avoid the CAN bus lines bypassing the effect of a common mode choke. And the pre-compliance test results show 20 dB reduction across the whole range to 120 megahertz. And then, of course, you can't really put this is just a diagnosis setup into the final design, but in the final design, we managed to make a small PCB. So the final EMC test result shows a good margin to pass the stringent manufacture limit. Now we want to touch the topic of grounding. 90% of the EMC issues we have seen so far is all more or less related to poor grounding in the system design. So if you find problems such as if you found by adding more capacitors, you find the EMC results actually getting worse, like a radiating emission actually shoot up, or your system is subject to various transient events such as bulk current injection failures or low voltage, high voltage transients, or your system is sensitive to ESD, then all of this perhaps indicates that you have a very poor grounding in your system. So here shows you why poor grounding system is bad for your system. this is a typical design in the automotive design. You always have a 0 volts reference. People call it a ground reference, or whatever they call it, but it's the 0 volts reference. And then you have the metal chassis, or the actual enclosure. Often this enclosure is bonded via a strap to the actual measurement ground plane. And if you have a high impedance joint connection between your 0 volts and your chassis reference, then it's going to be a big problem, because as you can see here, if I add more filtering capacitor, I will guide a lot of high frequency current into the 0 volts reference. And then through this high impedance path, this high impedance becomes a voltage source, and this voltage source will drive emissions up. That's why you find by adding more capacitors, the radiating emission went up. Here shows you a typical mistake that people make. So the pink or the what's the color of this trace showing here outside is a ring structure, and this is a large loop. It's a big inductance. Imagine if you call this a chassis reference, then surely you will have a big problem in your EMC test. This is the third case study in which we identify that unconnected ground planes act as patch antennas. So here's the test setup. This test setup you can find online. It's using directional coupler and spectrum analyzer that has a tracking generator function. So basically what it does is just sweep across a frequency range, and because you have a small magnetic loop here, most of the time the energy will be bounced back. So your spectrum analyzer see a sort of flat line. But if you happen to touch a structure that has a very strong resonance frequency, so the energy, rather than being reflected back, it will be absorbed by the resonance structure. So you will see a dip. So in this case, for instance, we identify on the edge of the PCB, that's where the TO247 PCB is mounted, we identify there's a very strong resonance point there. And then that actually aligns with the radiated emission test they did. And at that point, you see a big resonance peak there. So the lesson learned here is, if you have a structure that looks like a small antenna, or if you have, say, 6 layers of PCB, but on that area, your ground planes are not stitched up by vias, then chances are these will act as antenna, and you should avoid it. Yeah. Okay. So here comes the summary points. These are the points to take after this presentation. It's not only about the switching frequency that matters. More important is how fast the device switches that matters. Switching events are the major noise source in a electric system, and this is we can clearly see from many case studies. It is always easier to fix an EMC issue at the source side. When the noise propagates and couples through the nearby structures and propagates into the bigger system, then it's much difficult to contain. That's why you always try to hunt down where the noise source is. And never underestimate a seemingly small noise source. Sometimes you think, it's just a current sensor, but actually it can cause big problems. And ground design is perhaps the most important thing that you need to take into consideration, especially when you start a brand new design, completely new design. Yeah. And rethink your EMC risk during the R&D process. Okay, and this is the end of the presentation. Thank you very much for listening. I hope you enjoyed it. If you are interested, please share this video with your colleagues and subscribe to our video channel. Thank you very much.